Hello again. We continue with the Taylor polynomials. I want to show you here one example with approximation. Now, this is the question. Find the intervals for x, interval for x, so that here in absolute value cosine x minus this Taylor polynomial 1 minus x squared over 2 factorial plus x fourth power 4 factorial. So this difference should be less or equal 1 over 1000. So I told you that we can make the Taylor polynomial close to the function if we increase n, or if we make smaller the interval around the point where it's expanded. This is here the fourth Taylor polynomial for the cosine centered at 0. It's a partial sum of the Maclaurin series up to fourth power. We can write that cosine x minus t4x in absolute value. This is the absolute value of the remainder of order 4. Let's write good 4 here. And remember that the remainder of in the Taylor formula I shall write for any n. This is n plus first derivative at some point between x and a is where it's centered, in this case between 0 and x, over n plus 1 factorial x minus a n plus first power. And if the n derivative, the n plus first derivative in absolute value is less or equal to m, we have this Taylor estimate. The remainder in absolute value will be less or equal to m over n plus 1 factorial x minus a absolute value n plus first power. So in our case a 0 and n is 4. The fifth derivative of the cosine is sine. It's less or equal to 1, so m here can be taken for 1. So the remainder will be less or equal 1 over 5 factorial x fifth power. So this is the estimate, the value of the difference, and we want this to be less or equal to 1 over 1000. And we just have to solve this for x. Multiply this inequality here by 5 factorial, and we have this condition: x fifth power should be less or equal 5 factorial over 1000. 5 factorial, this is product 1, 2, 3, 4, 5, that's 120. And here we can reduce by 10, so this will be 12 over 100, and reduce by 2, 6 over 50, again by 2, that's 3 over 25. Taking fifth root, absolute value of x should be less or equal fifth root 3 over 25. And this number, I computed on my calculator, is approximately 0.654 and so on. Anyway, it's less or equal to 0.7. So if we take this interval around 0, x less than 0.7 and bigger than negative 0.7, we have this estimate. So for such x, we have cosine x minus this polynomial 1 minus x squared over 2 factorial plus x fourth power over 4 factorial. This will be less or equal than 1 over 1000 over this interval around 0. This polynomial we can simplify. We can rewrite this in the form cosine x minus 1 minus x squared over 2 plus x fourth power over 24. This will equal 1 over 1000 in our interval. So this is how we work with the Taylor polynomials. We estimate the remainder to see what approximation the Taylor polynomial gives. Now, I want to show you one applet which you can use to play with Taylor polynomials. And I shall send you the address of this applet separately. So here it is. This applet, it stays on the internet. You can choose a function. In the box here, it's cosine x. And then you can choose around which point you want this centered. And then you choose the degree of the Taylor polynomial. Here it stands at 4. And it shows you here general formula in the yellow box. And with specific coefficients for this function and this point. So you can see when you change n, increasing n, the blue graph is the Taylor polynomial, how it approximates the graph of the cosine. The cosine graph is the black curve. Increasing n, you get a better approximation, but it stands only around 2. Far away from 2, polynomial is very different. Let's go back here. You can see when n is 2, you have just a parabola. Then here is the fourth polynomial. Away from 2 here, there is a big jump. So this polynomial is not bounded, obviously. But close to 2, it approximates well. See again how increasing n, you can better and better approximation. And of course, close to this number 2, you have good approximation when x is close to a, 2 in this case. So you can use this applet to work with Taylor polynomials. And you can also show the absolute value of the error. This red line shows you the error. So the error is very small, close to the point 2, and far away the error becomes very big. Okay, so as I said, I shall send you the address of this applet on the internet, and you can use it for the study of Taylor polynomials. Goodbye for now.